They can move it to Saturday. Okay. Okay, hey, I'm going to continue on. We have 4 problems to cover today, 2 of which look identical to the homework, and then I'm going to intro one of the new problems we're going to be eventually getting.
Okay.
Question.
Do you think you could have passed the physical requirements to be an astronaut?
Yeah. When I was younger, yes. Not now.
Easily, though.
Yeah.
It's still good.
I would assume it would just be like a normal presidential fitness test.
Yeah, I don't think they would really require you to do that much, especially because of gravity.
No idea. So, okay. All right. Hey, let's continue on here. All right. Rate of change. We have homework due. We have homework today. It'll be due on Thursday. It's a worksheet. I believe there is 8 questions on it, and they're all based on graphs. So it'll be based on these really quick hitters, if you can find it. So, So here's the idea. Question. Your notebook? Yes. Right. All right. Okay. All right. Hey, okay, real quick here. I want to just kind of talk about just kind of some easy problems here. We'll start with something. Hey, quiet down. We're going to start with something easy, and then we're going to work our way to the more challenging problem. So let's say that this is my original function. This is a normal f of x. It's not a derivative. I'll give you a derivative graph on the next one. And the idea is that what we have to do on this particular problem is figure out if there's an inflection point, if there's any critical points, and I want to talk about the differences. Now, if you don't remember, shut up back there. Okay, critical points. That's first derivative. Once you find the first derivative and you find out where the first derivative would be 0, that would be your critical points. So it's basically the easiest way to do this, if you're looking at a normal function graph like this is a normal graph, you look at for wherever the slope would be 0. So in this case, this is where my first derivative would be 0. What number is that? -4. That's a critical point. Okay? Now, inflection points are where this thing changes from concave down to up or up to down. In this particular case, I will not have an inflection point. It's not going to happen. Just because what we're actually looking at here is we're looking at what? So if I were to like draw this here, this is a positive slope. So the numbers would be going up. It would hit 0, then it would go to negative slope. So in theory, if I were to like draw the first derivative graph, not quite. It would actually look like this. It would be positive numbers. It would come down to 0, and then it would be negative numbers, and it would go down this way. And the idea is that potentially, if this is truly the case, and again, what you're looking at here, this is the first derivative graph of what I'm going off of. Potentially, on this particular problem, I could have an inflection point right here again. Because if you look at this, it potentially goes from, changes directions. So that could be a potential inflection point. But when you actually look at the picture, is it truly an inflection point on that picture? No, there's not. And so that's the idea that it doesn't actually truly have an inflection because it didn't change from concave up to down. That's just kind of how I look at it. The first derivative graph it would show a potential though. The potential would, in fact I don't even have it drawn right. The potential here would be at -4. So the potential would be at -4. This would be -4 and 0 would be over here somewhere. Okay. And again, that's just the first derivative graph compared to the original, just because of what the slopes are doing. The slopes are positive, go to 0, then they go negative. So I'm kind of looking at a first derivative graph. And so my prediction is that this probably doesn't have an inflection.
Okay, so you know how derivatives are kind of related to like the velocity time graphs
yes.
compared to the acceleration time?
Yeah.
What would come after acceleration time?
We normally don't do that. I've never had to go. We never had to explain what a third derivative, basically what you're saying. That would be the acceleration of acceleration, right? Or so like, because every time you go, so like you have positional, you have, so the next derivative would be the velocity of that. Then after velocity, you have acceleration, right? and then you go after that, and so it'd be the derivative of acceleration, so it'd be the rate of change of acceleration, which we wouldn't really look at.
So like, what?
Like a fluctuation of force, wouldn't it be?
Kind of, yeah. It'd be almost the same thing. The only idea with fluctuation of force is that that's applied to first and second derivatives. It's not really like a third derivative, right? So it's just it's a rate of change of acceleration. So how hard are you pushing that pedal and how fast you let it go? Like what's that change you're making in that foot pedal?
Well, that's kind of just the acceleration.
Exactly. So that's why we don't really go past it. Okay. All right. Hey, let's move on. Okay. All right.
If you can't finish that.
Okay. Hey. This is one of the last problems I'm going to do, and then we're going to intro our next one. I had 3 or 4 problems picked out. I might only do 3 because I do want to give you time to actually get to your homework today. You have 8 problems, and I want to make sure you actually have time to work on it.
This is new homework?
New homework today, and it'll be due on Thursday this week. So what?
Over this?
No. It's kind of like we're doing here.
You won't like me.
All right. Let's move on to this one. So I'm going to give you a first derivative graph. The last one we did was a normal function graph. Let's do a first derivative graph, and I'll just kind of make it something like this. Kind of make it 2 changes. Again, this is just a random graph. This is a first derivative graph. Okay, it's not the normal graph; it's the first derivative. So on this particular graph, let me redraw this. I want to make sure. I want to make sure it hits 0. So let me make sure it hits 0. Okay, so I'm just moving it down a little bit. All right, first derivative graph. So on this particular problem, the critical points, and again, the critical points are where the first derivative is equal to 0. So where the function is actually 0. So in this case, we have 3 critical points. It's different than the normal functional graph. The function graph is where you look at where the peaks and valleys are, right? That's how you do it on a normal function. But this is the first derivative graph. So you're actually looking at where the first derivative is 0. That's what you have to have your mindset. Is this a normal function or is this the first derivative function? And so now that we have this, what are those numbers? We have a negative. Yeah, what is that? 1, 2, 3, 4, 5, 6, 7.5. So negative 7.5 roughly. Negative 1.5. And
Close enough.
3, close enough. And you just have to be in the ballpark. That's the beauty of doing these today.
No, the beauty of it is you.
All right.
So because you...
You're making him laugh. He's trying to ask a question. What? Come on, buddy. You'll get it.
Okay, so because this is like already the first derivative.
Yeah. So that's where we're just looking at where it hits 0.
Okay.
Yeah. If this was a normal functional graph, like if I didn't say this was the first derivative, and I just said this was the normal function, where the critical points are would be the peaks and valleys. If that was a normal functional graph. But since it's the first derivative, I want to know where it hits 0. Okay? All right, now, second derivative, this is where I can find potential inflection points. And yes, I have potential inflection points because it's where I'm actually changing. So on this case, it's where the second derivative, so this again, we're going inflection. So on this one, for the inflection points, I'm looking for where the second derivative would be 0.
That's where it hits the bottom of the slope.
So
0.
Yeah, so in this case, yes. So on this one,
You're wrong.
we're looking at these points on this particular problem. Since this is a first derivative graph, we're looking at the peaks and valleys now. If this was a normal function, if this prime symbol wasn't there, and we're looking at a normal function, I look at where it changes direction. It went from concave down to up. That would be the inflection
Where it
point.
changes direction. So that.
And so it's usually always halfway between the peak and valley. That's kind of where the inflection point would be. But in this case, this is a first derivative graph. So since it's first derivative, we're just looking at the peaks and valleys on this one. It'd be where that second derivative would be 0, and it'd be there. So that number here is what? 5, negative 5, and 1 or 2, 1.5. I'll say 1.5. You just have to be in the ballpark. Okay.
1.
All right. Now, this is kind of up to you guys. Do you want another one?
No.
Okay. And there's ways of checking whether it's true or not. I'm not going to have you test that today.
Is this what homework is?
This is what your homework is. That's it. It's those. There's nothing weird. I just give you a bunch of graphs, and you have to interpret what the graph is telling you.
Classroom, or are we doing?
Classroom. And so the beauty of it, all you're doing is you're typing critical points are this, inflection points are this. If you can find them, that's it. Do you guys need another one?
No.
Okay, you guys have the rest of the time you can work.
I thought you were going to intro something.